Hi, in this video we're going to look at the derivatives of the 6 inverse trig functions. And because we've skipped ahead a little bit to the end of the chapter and we're going to come back and do some of the other material next week, we haven't yet done the stuff that we would need to do that would justify why these derivatives are what they are. So we'll come back and we'll prove some of these next week. But for right now, what I want you to work on is making sure that you memorize these. Memorize these along with the other ones that we've worked on. There are some similarities that maybe makes it a little bit easier to memorize some of these. You might notice that all of them involve fractions with a numerator of 1, right? So if you can kind of just know they all start with that kind of form here. And then they have different denominators, and some of them, though, have similar denominators. So you might notice that the derivative of the sine inverse function and the derivative of the cosine inverse function have the same form on the denominator, a square root and then a subtraction in that order. One important thing to notice, though, is that the derivative of the cosine inverse function has a negative in front of that derivative. So just kind of noticing those relationships and patterns, if you can kind of remember the patterns and you have memorized the derivative of sine inverse function, that might help you remember the derivative of the cosine inverse function. And then the next two that are here in the chart, the derivative of tangent inverse and cotangent inverse, those also have the same denominator, and the derivative of the cotangent inverse function has a negative out front. On the tangent inverse and cotangent inverse, you might notice that there's no square root on the denominator of those. So that's a difference between that and the sine inverse and cosine inverse derivatives. Also, because on tangent inverse and cotangent inverse, you've got addition there in the middle, that you could have those terms on the denominator written in either order. So you could have x squared plus 1 instead of 1 plus x squared. For the subtraction ones, the derivatives that involve subtraction, though, remember order would be important there. Okay, and then for the last two, secant inverse and cosecant inverse, the denominator is the same on both of those. And don't forget those absolute values on the x that is outside of the radical. And then make sure that you pay attention to the order of the terms inside the radical and what order they're subtracted in. And again, just like all those other pairs, the derivative of the co-function, the inverse co-function, has a negative out front. So these ones probably take a little bit more work to memorize than some of the other ones we've looked at so far. So flashcards or just printing out a chart like this and then folding it in half and sort of using that as a flashcard, or fold it in half and practice writing them all down and then unfold it and check. But whatever you need to do to make sure you have memorized those. Okay, so for the rest of this video, we're just going to look at some examples of using the derivatives of those inverse trig functions to find derivatives of other functions, also using product rule, quotient rule, chain rule, whenever those things are necessary. So let's look at a couple of examples. Here we have one. So anytime you're finding a derivative of any function, one of the first things you should pay attention to is where is the variable. And so for this function, we have only one input variable. So if we want to find y prime or dy dx, I would notice that I have only one input variable. I have a constant times a function. So we have a rule that says when you differentiate a constant times a function, that constant just comes along times the derivative of the function. And then you have to remember the derivative of the sine inverse function. So you might pause the video, write down what you think it is, and then start the video again and see if you have the same thing I wrote down. Okay, so there is the derivative written in one form, one way you could write that, and it's perfectly fine to leave your answer like that. There's a couple other ways that you might write that answer. I could think of this as negative 5 over 1 times 1 over the square root of 1 minus x squared. And so I could just multiply straight across on the numerators and write that as negative 5 over the square root of 1 minus x squared. That would be okay too. That's really about it on the simplifying though. There's not much else you can do. Sometimes I see students try to square root both the terms on the denominator, but square roots don't work that way. You can't distribute them across addition and subtraction. You could graph that function and graph it without the square root if you square root both terms on the denominator and see that they're not the same function. So if you're tempted to do that, you need to resist that temptation. Okay, we'll just look at a couple more examples here. Okay, so this next one, really just kind of straightforward function here. I have y equals secant inverse of, and then I have x to the fifth. So I only have one place where I have an input variable. And so I just kind of need to think about this. I need to remember the derivative of the secant inverse function. And then I also need to notice here that I don't just have secant inverse of x, I have secant inverse of a function of x. So on this one, I'm going to be using chain rule. I have an inside function, which is the x to the fifth, or I'll put inner here, and then the outer function is the secant inverse function. All right, so the derivative of secant inverse is a little bit more complicated. I'm going to write that over to the side here. So the derivative with respect to x of secant inverse of x is 1 over the absolute value of x times the square root of x squared minus 1. Okay, but what I am working with here is not just secant inverse of x. I have secant inverse of something else. But I want to think about that derivative, that basic derivative that I know, and then really it's just a matter of applying chain rule to the problem we're working on. All right, so for the problem we're working on, I'm going to write y prime, or dy dx, equals, and then I need the derivative of the outer function. So the derivative of secant inverse of something is over here, but instead of just x in the function, I'm going to have x to the fifth. So everywhere in this derivative where I have an x, I'll actually be putting x to the fifth in for this problem here. So I'll have 1 over absolute value of x to the fifth times the square root of x to the fifth, the quantity squared, minus 1. All right, so that is the derivative of the outer part, taking the derivative of the secant inverse function. So the derivative of secant inverse, I use this, leave the inside of my original function alone. And now I need to take that times the derivative of the inside function, which would be the x to the fifth function. Looking back at my original function, what is the inner function here? All right, so times the derivative of the inner function, I'll have times 5x to the fourth. All right, so I'm going to do some labels here. This first parentheses was the derivative of the outer part. The derivative of the secant inverse part, leave the inside alone, then times the derivative of the inner part. So that was chain rule. So at this point now, I could leave my answer like that if I really want to. I could also do a little bit of tidying up here, so I'll do that. There's a lot of algebra in this problem to tidy it up. I might start by writing 5x to the fourth over absolute value of x to the fifth. And then inside the radical, I have x to the fifth, the quantity squared. So there's a property of exponents that I need to use there. A to the m to the nth power. So the rule is that you multiply those exponents. If you just kind of think about what that means, it's x to the fifth squared means x to the fifth times x to the fifth, which would be x to the 10th. All right, so the main thing I did in simplifying that was I simplified the x to the fifth, the quantity squared, as x to the 10th. All right, the other thing that you might notice that you could probably do here is cancel some x's. And so I have x to the fourth on the numerator, and I have an x to the fifth on the denominator, and I can cancel those. I need to be a little bit careful because of the absolute value. So I'm going to write out an extra step here just so you're clear about what's happening here. So when I do that canceling, I'm going to split that x to the fifth on the denominator up into an x to the fourth times an x. And I'm going to put absolute values around both of those. So you can split the absolute values up like that across multiplication, not across addition and subtraction. Okay, so then the other thing that I might notice is that because of the even exponent, x to the fourth is not ever going to be negative, so the absolute values don't really do anything on that x to the fourth. So I can drop the absolute values on the x to the fourth part and then cancel with the x to the fourth that I had on the numerator. So another way I could write my answer is 5 over the absolute value of x times the square root of x to the 10th minus 1. So that is a simplified version of the answer. Don't forget that absolute value there. Simplified version of the answer. The thing that I had in my very first step is actually a correct answer as well. It's just not tidied up as much as what I have here at the end. Okay, let's look at one more example. So when I look at this one, I'm going to notice that I have x's in a couple different places here on the right-hand side. So unlike the previous problems here, I'm going to have to think a little bit harder about that. So if I read the right-hand side, it says x times cosine inverse of 5x squared. So I've got a product, x times cosine inverse of something. And then I also am going to have a chain rule going on here, because on the cosine inverse part, I don't just have x inside the cosine inverse function. I have a function of x inside the cosine inverse function. So on this one, I'm going to be using both product rule and chain rule. The overall structure of the problem is product rule, but when I go to take the derivative of the second part there, that is a function within a function, so I'll need to be a little careful with that. All right, I'm going to just go ahead and do this one. Hopefully you're good enough at these derivatives now. You're maybe not needing to set up so many labels, but if you do need to set up labels, that's okay. I'm going to say out loud what those labels would be. Okay, so y prime equals derivative of the first, so the derivative of x is 1, times the second, plus the first. Okay, and then here, when I take the derivative of the second, that's where I'm going to need chain rule. So I'm going to go over here to the side and write down the derivative of the cosine inverse function. You need to remember that, and since that's new, we'll go ahead and write that down. That's one of those that has a minus sign out front. Negative 1 over the square root of 1 minus x squared. Okay, so I need to remember that, and so when I find this derivative, I'm going to have negative 1 over the square root of 1 minus. And then what I have here, though, is not just x inside the cosine inverse function, but 5x squared. So I'm going to be putting that whole 5x squared into that derivative in place of x. So when I do that here, I'll have 5x squared, the quantity squared, right? That's the derivative of the cosine inverse part. And then I need that to be times the derivative of that inner function. That inner function is the 5x squared. So the derivative of 5x squared is 10x. All right, there is an unsimplified version of the answer, which would be okay, but sometimes you're probably going to want that tidied up if you're going to do anything with that derivative. So before the plus, 1 times cosine inverse of 5x squared just simplifies to cosine inverse of 5x squared. And then after the plus from product rule, I have a whole bunch of stuff here, and that stuff's all times each other. It's all just one big term, so I'm just going to kind of think about what I want to write out front and what I want to put on top of a fraction and what would be on the bottom of the fraction. Okay, so I have a negative sign here, so instead of writing plus and negative, I'm just going to make that minus. And then on the numerator, I'll have x times 1 times 10x, so 10x squared. And then on the denominator, I'll have this radical, and I'm going to go ahead and simplify the 5x squared, the quantity squared, so that would be 25x to the fourth. Don't forget to square the 5 that is in that. So this 5x squared, the quantity squared, means 5x squared times 5x squared. So that's where I get that 25x to the fourth in my answer. Okay, and that's it. That's really all the simplifying I can do. So there is my y prime. All right, so next week we'll look a little bit at how we got those derivatives that were in that chart, like where those fractions came from and all of that stuff. So we'll look at proving those next week. For right now, I just want to work on memorizing them and practicing using them.